Imagine this. A model stares at millions of sentences, one word at a time, and slowly begins to predict what comes next. At first, it's random. Then it starts guessing patterns. At billions of predictions, it begins to write reason, and even it can chat with you. But how does that happen? What is the math that turns prediction into understanding? And how the AI modeled the understanding for itself to understand your meaning? That's what we are uncovering today. Let's start simple. Every large language model from GPT to LLaMA has just one job: predict the next token. And that's it. No magic, no hidden logic, just the probability of the next word given all the previous ones. Formally, we can say that it's basically the conditional probability like what you see in the screen. That is the entire training objective. And yet, this single goal is so powerful that it's enough to teach the model grammar, knowledge, reasoning, and style. Let's take an example. We show the model a sentence like "the sky is blue." During the training, it never sees the full sentence at once. It sees partial snippets and tries to fill in the blank step by step. When the input is there, the target will be sky. When the input will be the sky, the target is, and so on and so forth. Each time, the model predicts the distribution over possible the next tokens. It might think that blue has 75% chance, dark is 10% chance, clear could be 5%, and green is 2% chance, and so on and so forth. We compare that prediction to the correct answer, which is the blue in this case, and we can measure how far off it was. The measurement becomes loss. In machine learning, loss means how wrong your model is. For LLMs, the most common metric is cross-entropy loss. It measures the difference between the predicted probability distribution and the true one-hot label. The one-hot label means that the correct tokens. Formally, you can show it like this. Of course, you don't need to understand this equation here. What it does basically, for the yi is 1 for the correct token and 0 for others, and the y hat is the model predicted probability for that token. If the model predicts 99% for the correct word, the loss is tiny. If it predicts 1%, the loss is huge. So model's goal is simple: minimize loss by predicting the correct word more confidently. But knowing you are wrong is not enough. You have to learn from it. That's where backpropagation comes in. Backpropagation is the process that adjusts all the knobs inside the model, which includes billions of parameters, so that next time it is a little less wrong. Here's the cycle. In the first step, model makes a prediction. We compute the loss in the next step, and backpropagation calculates the gradients. The gradients is the indication how each weight contributed to that specific loss. Then in the fourth step, the optimizer adjusts those weights by taking a smaller step into the opposite direction. This process repeats millions of times. That's how raw numbers slowly shapes into the intelligence. The algorithm that drives this process is called gradient descent, and it's modern variants of like Adam algorithm or Adam W algorithm. At each step, we update parameters like this. So imagine it's like a theta. Theta here represents the model parameters. Eta, on the other hand, is the learning rate. It's basically how fast you want your mistakes to be faded from your model. And the partial derivation of the loss against the theta is the gradient of the loss with respect to the parameter. Each step is very tiny, but repeated billions of times. That's how the model fine-tunes its internal map of language. And this is the training loop, the endless cycle that teaches LLMs to predict words, then sentences, then paragraphs, then eventually everything. So the question comes into the place is that why next token prediction works so well? At first glance, predicting the next word sounds trivial, but think about what it requires. To predict the next word correctly, the model must understand grammar and syntax, word meanings, common sense, even facts about the word. If the prompt says the capital of France is something, the only way to get that right is to know Paris. That's not memorization. It's pattern learning at massive scale. Next token prediction forces the model to learn structures, semantics, and relations all at once. When we scale everything like more layers, more data, more compute, some abilities start to appear. The model doesn't just predict syntax anymore. It starts to generalize, reason, and analogies. This is the magic of a scale. Simple objectives, but complex behavior. That is why modern LLMs do not need explicit programming for tasks like translation or summarization. They just learn them through exposure to enough examples. So data is a key here. These models are basically trained on trillions of tokens. Those tokens include books, articles, code, conversations, or all essential information throughout the internet or in the libraries. Each token is one more example of how humans use language to express their own thought. By minimizing loss across such a massive dataset, the model gradually builds an internal statistical model, which shows that how words, ideas, and facts they're connected with each other. That's what allows it to answer, generate, and reason all from predicting one token at a time. After months of training and trillions of updates, the loss curve drops and something interesting happens. The model starts completing your sentences, then your paragraphs, then even your thoughts. It's no longer just machine patterns. It has learned the structure of the language itself. All of that from one simple equation. It needs to minimize just this value. Now that our transformer knows how to learn, how does it speak? How does it decide what word to generate next when it's writing from scratch, without having any prior knowledge about the correct answer? That's where we are going next. If you have any questions or any points to make, don't forget to comment down below. Until the next video, good morning, good afternoon, good evening. Bye.